Okay, so let's work through this. We're given that the tangent is 24/7. We're going to use that to try and fill in the triangle. Again, I'm just going to give myself a little sketch of a right triangle. It genuinely does not matter which corner you use as your theta. It does not matter because we're kind of putting everything relative anyway. On Friday, I put the theta down here. That's the only reason I put it up here. It's just so you practice having it be different places. It's always going to be one of the smaller angles. It's not going to be the 90. This will never be our theta. That's just part of the definition of what we're doing. So I'm going to use this one. It feels weird. Most of the time we do use this one, but I'm just putting it here because it doesn't really matter when we're looking at these pieces here. So if we're looking at this as our theta here, that means this side is what kind of side? The adjacent. So this is our adjacent side. And this is going to be our opposite side. Because this one is always the hypotenuse. So when you draw your triangle, I highly recommend that you think through those pieces before we start looking at the numbers. Because tangent is made of which pieces?
Opposite and adjacent.
Yeah, remember SOHCAHTOA. TOA, opposite over adjacent. So this is our opposite over our adjacent. So the opposite side has a measurement of 24. So this is 24. And our adjacent side is 7. So how could I figure out how big the hypotenuse is? Yeah, use the Pythagorean theorem. Our a squared plus b squared equals c squared. Well, our legs are the a and b, so it doesn't matter which one it is. So I'll put it as 24 squared plus our 7 squared equals that hypotenuse squared. So what is 24 squared? 576. How much is 7 squared? 49. So we get 625 is c squared. So what does c equal? 25. So 25 is c. And we know the measurement of our hypotenuse. It'll let me zoom in. There we go. My iPad likes to be a grumpy Gus. Okay, so we need to have all of our sides before we can do our all 6 trig functions. So then we have our sine of our theta. Sine is made of which two pieces? So OH, opposite over hypotenuse. So our opposite has a measurement of 24. Our hypotenuse is 25. Our cosine of theta Yep, you're exactly right. It's our adjacent. Ca, C-A-H. Adjacent over hypotenuse. So our 7 over 25. And then our tangent of that angle is going to be what? Our 24 over 7. And that's a good way to double check that we've got everything set up right, because TOA, opposite over adjacent, 24 over 7. And that's exactly what we were given, so we definitely have this all set up right. So we're in good shape there. So those three we're usually significantly more comfortable with. When we're looking for our other three, remember that each pair gets a single set of co. So sine is going to go with cosecant of theta. Our cosine goes with secant. And tangent goes with cotangent. So each set gets one sine and cosecant. Cosine goes with regular secant, tangent and cotangent. So I know these guys go together, but how does that help me find this value without having to do anything else? They're reciprocals of each other. So they're upside down. So cosecant is going to be 25 over 24. They are reciprocals of each other. Be super careful with things. They're not technically inverses. They are reciprocals. So our secant is going to be what? 25 over 7. And our cotangent? 7 over 24. Okay. Questions there? So that's kind of how we finished up on Friday, was with one like that. When they give us information, they give us measurements. That's super duper awesome. There's a couple of kinds of problems that they give us that they love to word things super weirdly. So we're going to look at a couple of really weirdly worded ones. They're not super wordy. They're just weird to wrap your brain around. We're going to do, and I promise there's a reason. So we're going to find the 6 trig values of an isosceles right triangle. That is the information they're giving us. So any kind of generic isosceles right triangle. So we're looking at some triangle. We know it's going to be a right triangle. What do we know about isosceles triangles? Yeah, the two sides are the same. So isosceles right triangles means this side's going to be our right. Our hypotenuse is always across from the right angle. So this side and this side are exactly the same measurement. So this is still our hypotenuse. And then our sides, they're not telling us how long they are. So we're just going to pick a variable. I'm just going to call them x. So this side has a length of x and this side has a length of x. But the important thing about isosceles triangles is that these two angles are exactly the same. That's what makes it isosceles, is these two sides are the same and these two angles are the same. So it doesn't really matter what or which angle we pick to be our theta. What would be the degree measurement of this angle? Yeah, both of these are going to be 45 because this is a right triangle, so this guy's 90, which means these two guys, when they're exactly the same, are both going to be 45 degrees. So I'm just going to pick the bottom one to use as my theta just so we can think about things the same way. But we also know that our theta is 45 degrees. It just is. Because of the fact that it's an isosceles triangle. It's just one of those little things that we know. So if I know both sides are x's, just because I picked an arbitrary letter for some random isosceles triangle, how could I figure out how long the hypotenuse is if I know these pieces? Kind of. We know those pieces kind of, right? Same vibe as the last one. Yeah, we're going to do our a squared plus b squared equals c squared. It's still a right triangle, even though it's isosceles. So we're going to substitute in our pieces. We're going to have our x squared plus x squared is c squared. What does that simplify down to be? 2x squared is our c squared. So what is c going to be? Ooh, super careful. Because if I square root both sides, I'm with you on the x. But what happens to that 2?
Under the c.
It's still under the radical, square root of 2. So you can do it as x times square root of 2 or square root of 2 times x, either way. But I can't just make this magically be a positive 2. This is square root of 2. So our length on our hypotenuse is x times the square root of 2. So it's icky and gross, but I promise you. No, it's just going to be congruence. It just kind of is. So even though we don't have the lengths on any of these sides, I can figure out what my hypotenuse is. It's just using this as kind of our basis. We still can find our trig functions on this. We're still going to do this. So if I find my sine of that angle, again, I'm just using this one. I picked one from arbitrarily. Either one of these angles is fine. So then we have our opposite side over here and our adjacent side over here. What is sine going to be? What is the opposite side? X. What is our hypotenuse? X times square root of 2. What does that simplify to be? 1 over square root of 2, right? Because those x's cancel out. Do we get to have square roots in the denominator? No, we're going to rationalize it. So this is going to be what? Square root of 2 over 2. So it doesn't matter how big the sides are. When we're looking at our trig functions, if I have a 45 degree or as like if we put it in radians, it would be r pi over 4, the sine is going to be square root of 2 over 2. It doesn't matter what the side length is because it's all based on that angle. So let's do the same thing with our cosine of theta. What's our cosine going to be? It's going to be our x over our x square root of 2 again. So again, those x's are going to cancel out, and we get our 1 over the square root of 2, which again rationalizes to the same exact darn thing, that square root of 2 over 2. Then let's do our tangent. What do we get when we set up tangent? It's our opposite over our adjacent. So our tangent is just 1. X over x, they simplify down. So it's weird because we have letters in there, but they're all kind of canceling out. So questions on these 3 before we do the other 3? Just because I know these are weird. And I get that. Okay. So let's do our partner ones that go with it. I'm going to put them down at the bottom just because I'm going to run out of space if I don't. So if we do our cosecant of theta, what are we going to have?
2 over square root of 2.
Yep, you can either take this one and do our reciprocal there. Then we'll have to re-rationalize. We could also come back to this part. If I take the reciprocal here before I rationalize, then I don't have to rationalize again. So we can do our square root of 2 over 1. That's absolutely valid, and that our cosecant is square root of 2. It's 100% valid if you take this guy and do the reciprocal. You're just then going to have to re-rationalize, and then your 2's are going to simplify out. So you'd get the exact same answer. You're just giving yourself an extra step of rationalizing. It's totally fine. It's just a little bit more work. What are we going to get for secant? Square root of 2. So again, because again, we'll come over here and we'll take our reciprocal right here before rationalization. And we're going to take our reciprocal, square root of 2 over 1. So our secant is square root of 2. What about cotangent? It's just going to be 1. The reciprocal of 1 is 1. Okay, so our sine, cosine, tangent. It doesn't matter if we don't know the side lengths, really. If we know things about the angles and we know some of the relationships, we can find all these values extremely accurately without even knowing the side lengths. These values here, especially these 3, are going to be super important to us, and I will show us why in a little bit. But these 3 are going to be super duper important to us. Okay, questions on this one? We're going to do another really weird one. Okay, very much like this. I promise there's reasons. Because we're going to look at a 30, 60, 90 right triangle. And we're going to look at a whole bunch of things about it. But first thing I'm going to do is I'm going to draw me a 30, 60, 90 right triangle. I'm going to draw it like this. So I've got here my 30 degrees, and this guy is my 60 degrees. What's tricky to picture with our 30, 60, 90s is that they're not giving us anything about our sides. However, if we think about this being a half of, and I'm going to change my color real quick. Like this. If this is also 30 and 60, this outer triangle here, what do we know about this? If all three angles of this triangle are 60, what is this? It's an equilateral. So if we think about it being 60, 60, 60, then I know that this side, and this side are all the same, right? So if I know that this side and this side are the same distance, what is this in relation? It's half of it, right? Because this is the whole thing, and it's two of them here. So what we're going to do to label these sides is I'm going to call this bottom one some unit. Maybe I'm going to use a pen and call it x. But that means this side is going to be twice that. This is going to be 2x. So when we have a 30, 60, 90, we think of it as half of an equilateral. So we're still thinking about this little black triangle here instead of now the big gray one. So if I know that this bottom side we're going to call x because it's half the length of this side. Which piece of my 30, 60, 90 is this guy? That's my hypotenuse. This is one of my legs, and we're trying to find our other leg. So we're going to use our Pythagorean theorem again. It's going to be one of our good buddies. So we're going to take our a squared plus b squared equals c squared. We have one of our sides as an x. We don't know the other leg, but we do know our hypotenuse, which is 2x. Does everyone see where those pieces are coming from? Because I know there's a whole lot of weird there. Okay. I'm gonna say it's a whole lot of weird, and it's just one of those, they make it too complicated kind of dealios. But that's where this is coming from. So we are gonna try and simplify this out. I know that my x squared plus b squared equals 2x as a quantity squared. So what is this really equaling over here? 4x squared. What do I do to try and figure out what b is? Subtract x squared. So we're going to have that our b squared equals 3x squared. So what is b going to be? Yes. So our b is going to be x square root of 3. So this height over here is going to be x times our square root of 3. So I'm going to draw that triangle again just so it's out of our way and looking at things over here, just so we can label things the way we have been. That is not a great 30-90 triangle. All right. So just so we can label things. So I'm calling this bottom side is going to be x. This side was, our hypotenuse was 2x, and this is x square root of 3. And then they've asked us to actually do our 6 trig values twice, because we're going to do it for our 30 degrees and we're going to do it for our 60 degrees. So let's start with our 30 degrees, this guy. I'm gonna call this one our theta. So let's do our sine of theta, where our theta is our 30-degree angle. So we're looking at this guy. So how are we gonna set up sine? X over 2x. So sine of 30 is x over 2x. What does that simplify down to be? 1/2, yep. What about for our cosine of that theta?
X squared root of 3.
Mm-hmm. Yep, so we're gonna have our x square root of 3 over 2x, and that's gonna simplify down to be square root of 3 over 2. Gorgeousness. And then our tangent. What's tangent gonna be?
X over X squared root of 3.
Yeah, x over x squared root of 3. Sorry, my brain stopped there for a second. So again, those x's are going to cancel out. We get our 1 over square root of 3. We don't get to keep square roots in the denominator, so what is this one going to be rationalized? Square root of 3 over 3. Questions on those first three? Okay. So then let's do our reciprocal pieces. So our cosecant of our theta is going to be what? 2 over 1. I'm just going to put it as 2. Our secant of theta is going to be what? 2 over square root of 3. We'll need to rationalize that. And that's going to be our 2 square root of 3 over 3. Because we got to rationalize it. And then our cotangent one is going to equal, yeah, it's just going to be our square root of 3. If we take our reciprocal right here, it makes it easier so we don't have to do the recalculation. We did a whole lot right there. Questions on that one? Okay. So then we need to do the same thing for our 60 degree. So we've called this angle our 30 theta. So I'm going to use a different letter for this guy. I'm just going to pick one. That's going to just pick alpha. So we're going to do our alpha with that 60 degree angle. And we're going to do the same vibe. We're going to do our sine, cosine, tangent, and then do our 3 reciprocal identities. So our sine of alpha of that 60 degree angle is going to be what? That's what I named my 60 degree angle. Because we use Greek letters when it's angles, so I used theta for my 30. They wanted us to do both angles, so I had to find another name for it. You could put the 60 degrees if you want to and write it that way. I'm just going to write that down. So I could write this as sine of 60 degrees if you want to do it that way. Totally valid. I'm just going to practice writing the Greek letters because we typically name those things. So all that's going to do is change which side's my opposite and which side's my adjacent. It's the only difference. So our sine is going to be what?
X square root of 3 over 2x.
X square root of 3 over our 2x. And that's going to simplify down to be our square root of 3 over 2. Our cosine of that same angle, so I'm just calling it alpha. I made that up, made up the name. Is going to be what? What's our cosine? Bless you, going to be. Bless you.
Thank you. 1/2.
Again, that's going to be our x over the 2x. That's our adjacent over our hypotenuse. And the x's cancel out, so we get our 1/2, or 1 over 2. Tangent. Careful. TOA, opposite over adjacent. So that's our x square root of 3 over x. Our opposite side over our adjacent side. So that one simplifies down to just be our square root of 3. Yeah. And then, oh, I'm going to run out of space on here, but that's okay. Let's do our cosecant of alpha. What's our cosecant going to be?
2 times
Mm-hmm. So 2 over the square root of 3, which we're going to rationalize to be our 2 square root of 3 over 3. How about secant? That's the reciprocal of our 1/2, so that's just going to be our 2. And then our cotangent, yes, that's going to be our 1 over square root of 3, which we're going to rationalize exactly to be our square root of 3 over 3. So there's a whole lot of information up here. What do we notice that's the different and the same about our 30 degrees versus our 60 degrees, especially looking at our main trio, like our sine, cosine, tangent, looking at these guys compared with these guys? What do we notice?
Sine and cosine.
The sine and cosines are the same values. They're just switched. Okay? Those pieces are going to be super duper important for us, especially the sine and the cosine. Because these sine and cosine pieces are actually going to be our parts of our ordered pairs for our unit circle. We just calculated all the ordered pairs we needed for the unit circle. We just have to figure out how to put them together. So I have here a little table that we are going to fill in with some important pieces, and I've decided as of this exact second to make it significantly smaller, just because we don't need the other pieces. Hang on, just doing an adjustment real quick. Boop. Just cutting a piece off here. All right. So I'm going to pass out this little table here, and we're going to fill in some information. And we're going to probably look back at these. And I've cut off the secant, cosecant, and cotangent. So we're just going to do the sine, cosine, tangent. And we're going to look at some of these degrees. And these are going to be in our unit circle. So I made you guys this little table. It's going to be small. You probably could have drawn it by hand at this point, but I think I can. So I'm just giving it to you so you can fill it in. So we're going to start by looking at these 3 radiant angles. So we've got pi over 6, pi over 4, and pi over 3. These are angles we are going to work with bunches and bunches and bunches. So the first thing we need to do is we need to figure out what these are in degrees.
Here's what I found.
I'm not talking to you. Oh my gosh, she's so nosy. We are not going to use these. I'm just deciding this as of right now to cut these off. Oh, except I wanted to do tangent still. There we go. I cut this off. You guys don't even have these anymore. Nope. I made that choice all of 30 seconds ago. All right. So the first thing we need to do is we need to figure out what these are in degrees. How do I switch pi over 6 to be degrees? So if I take my pi over 6, I'm just going to put it over here, and we multiply it by our 180, over pi. That switches us over to degrees. So what is pi over 6 in terms of degrees? 30 degrees. So pi over 6 is the same thing as 30 degrees. Well, we just did 30 degrees on the last triangle. That was our theta. This guy was 30 degrees. We did this with arbitrary sides, so it doesn't actually matter how big the side is. We find those values. So the sine of 30 degrees is 1/2. Well, I ask us the sine of 30 degrees, which is also the same thing as pi over 6. It's going to be 1/2. We did that over here. Same triangle. So the cosine of 30 degrees is what? Thetas are 30 degrees. Where's our cosine of 30 degrees? Square root of 3 over 2. So cosine of 30 degrees is square root of 3 over 2. Our tangent of 30 degrees? Square root of 3 over 3. So no matter what the length of the side is, we have all the information here we need to find this information. So let's do the same thing for our pi over 4. Let's find that in degrees first. Pi over 4, switching this back to be degrees,
45 degrees.
is going to be 45 degrees. We done 45 degrees today?
No.
Yes.
Yes.
We did sometime today. All right.
Did we do 45 degrees?
I forgot.
We did. On the very first, not the very first one, the second one we did. The first one that had the weirdness where we didn't actually give you a side measurement because it doesn't matter how big the side is when we're looking at the relationship between the angle and the radius and the side length, because no matter what the radius is, it's relative. So these are the values for 45 degrees. Oops, there we go. So our sine of 45 degrees is the square root of 2 over 2. Our cosine was exactly the same, the square root of 2 over 2. And our tangent?
1.
1.
The next one's 6.
I'm going to say, so we have our pi over 3, our third one here. Converting in the same way, just so we can see it. 180 over pi. Is going to be what? What's our degrees? 60 degrees. Oh, snap. Have we done that one too? Wasn't that alpha? This one. We did our 30. We did our 60. We did our 45. Okay. So these are our values here. So we're 60 degrees. We had our square root of 3 over 2. Our 1/2. And then our tangent is exactly the same as the one from 30 degrees, which was our square root of 3 over 3. Oh, no, it was square root of 3. Sorry. I messed up. There we go. I marked it wrong and I had a Post-it note over the top. What these are for and why we wrote them in a table and why I care about these random ones that we did off these random triangles is these, in particular, these 6 values here, you will write a gabillion and a half times this semester. These will very commonly be answers that we use, and these 6 pieces are the ordered pairs for our unit circle. So on our unit circle, when we're thinking about this, if we think back to the one we started filling in last week where we had our degrees, where we had our 0 and our 90. And in fact, I'm going to zoom in so we can just see our first quadrant because I want us to just look at the first quadrant. When we filled in our degrees, this one is 30 degrees, this one was our 45 degrees, and this was our 60 degrees. Again, that's our pi over 3. Nope, pi over 6, excuse me. Pi over 4, and our pi over 3. When we're looking at our ordered pairs, what they are, and I'm double, triple checking before I give you something wrong. I just want to make sure my brain doesn't flip-flop on us. Is that our x's are the cosine of the theta, of the angle. Oh, that is not going to fit there. That is way too big. Sorry. So our x's are the cosine of the angle, and the y's are the sine of the angle. So for our 30 degrees, that's when we had our cosine being the square root of 3 over 2, and our sine was 1/2. For 45 degrees, that was when we had the square root of 2 over 2 and the square root of 2 over 2. Our sine and cosine were identically the same. For our 60 degrees, that was when it was switched from the 30. We had our 1 over 2 and our square root of 3 over 2. What we're looking at here and why it's called the unit circle is we're looking at this in a ratio of the sides, that arc length, to our radius. And since we're calling it a unit circle, what we're doing is a radius of 1. So that means my ordered pair here is on my x-axis, just 1 unit over. So we are at the point 1, 0 here. And on our 90 degrees, we're at 0, 1. So our ordered pairs are always going to be cosine and then sine. And what's really cool about the unit circle is since everything is kind of based off of this first quadrant, those 6 values will actually fill in the rest of the circle. These reflect. The difference between quadrant 1 and quadrant 2 is if I bounce this over here, which value is going to be negative, my x or my y? My x. So our 60 degrees, when it matches up with our 120 degrees, let's see, green, where's my green? Our 120, it's just going to be that our x's are negative. So we're going to have negative 1/2 over our square root of 3 over 2 is still positive because my y's are positive. When we look at our 45, which matches up with our 135 that was over here, again, my x's are the only thing that's negative, so we have our negative square root of 2 over 2 and a positive square root of 2 over 2. They match up. They line up. That was not the laser pointer. They match up. The only thing that's different is that my x's are negative. So same thing down here with my 30 degrees and my 150. My x's are going to be negative. So my negative square root of 3 over 2 and my positive 1/2. These also match up. What's going to be different down in quadrant 3? Both are negative. What's going to be over here? Which pieces are negative? My y's are negative, but my x's are not. Same values. They still match up, just because we're close on time. So my over 6's all match up. They just have a change in sign. My green. Oh, that's not the right thing. These pieces are going to have the same values, just with sign changes. And then these guys are going to have the same pieces, just with sign changes. So we have those degrees and radians from last week, and now we can fill in all those ordered pairs. So we have all the information we need to it. Our ordered pairs are going to be cosine and sine. So in our quadrant 2, we have that the cosines will be negative. In quadrant 4, sine will be negative. And in quadrant 3, both are negative. Okay, we're going to use all of that information, but that gets you the entirety of your unit circle. Because remember, this is something we need to memorize. But those are all the pieces we have for our unit circle. And that gets you everything you need to do to finish out that first homework on 6.2a. That's everything in 6.2a. We have less than a minute to the bell. There it is. Hey, I was technically correct. There's all that information. Have a great rest of your day. Yes, dear.
Where do I turn in the actual credit?
Oh, into the same place you turn in homework, into that homework, right? Yep.